Okay, recording started. For now, I don't share the screen because I'm not ready yet. Let me just open a web window. Okay. Okay, here we are. Good. Okay, how are you doing? Everything is fine. Do you have any question? Okay, very good. I just wanted to ask you once again if somebody of you is also attending the other course that I'm teaching now, Science of Climate Change. Raise your hand if you are. No, nobody. Okay, very good, because there is some overlap which I can't avoid because the other course is for students also from other degree programs. Okay, but it's no problem if you know it seems that nobody is taking both of them. I know that somebody is, but if you are only a few, it's okay. Good. So I'm sorry for last Thursday if the audio was not okay, and actually I realized I'm not sure if the video is still with the audio that is not okay. I hope not. I didn't check. In any case, I hope that you didn't lose anything important. If there is some gap, some misunderstanding, something that I need to explain again, let me know. Actually, I want to, I'm sorry, I need to switch the phone off. Actually, I am continuing today with some topics that I started on Thursday. And so I think there will be the opportunity, if you have any question, on what I lectured on Thursday to interact. Okay. I just wanted, before I start, to remind you that there is the opportunity for you to give presentations. I'm not insisting for now. In about a couple of weeks, I will become more insisting because I think it's a good opportunity. Of course, you need to get a figure, a picture of what we are talking about, but I think that once again that it would be a nice opportunity for us to interact. So what I am planning to teach today? Today, I want to make a first introduction to some modeling in quantitative terms. Quantitative terms means some also mathematical treatment. And don't be concerned. And so far my lecturing has been mainly narrative, okay, with no equations, not many technical details. I think it's time to get into some, indeed, technical development because this is a course focusing on adaptation. Adaptation means also making some projects, and the projects usually, as we know, need the support of modeling. And I think that we need to know some more in terms of modeling and in terms of how models are structured. So what are the fundamental bases, the theoretical basis, because this allows us also to better understand what is our true capability to predict the future climate. And we need also to get into the mathematical development, because getting into the mathematical development, you understand what are the processes that are reproduced, what are the processes that are not reproduced, in order to clarify that we actually, as I mentioned several times, we are not able to make perfect predictions of the future, like in any discipline, but in climate and climate-related processes more than in other disciplines of engineering. So, as you know, there are some of you, you know better than me, that are attending the degree programs that are not engineering programs. So don't be concerned, because I will clarify during these, let's say, quantitative lectures. I will clarify what I am asking at the exam to engineering students and non-engineering students. So if you are a non-engineering student, don't be concerned. I think the information is anyway useful for you, but of course, you don't need for your exam to learn in detail everything that I teach. I will try to be very clear. So what I'm talking about today, let me just open the lecture and let me share the screen first of all. Yeah. Okay, here we are. Okay, let me open the link that we dealt with the last time, Earth system. Okay. During that lecture, as you may remember, we talked about mathematical models. Just 1 second. Okay, here we are. We talked about mathematical models of the Earth system, and we talked about process-based models versus empirical models. We talked about deterministic versus stochastic models, but we didn't get into any detail about the underlying theory. So I updated this lecture and I added this section, mathematical structure of models. Let me just, enlarge it. And this is what I want to teach today. This is new, as I said. You will find it in the website now. I don't have a PowerPoint yet for this. I will teach on the Blackboard the details. And if you see anything that is not clear, as I said, this is new, developed during the weekend. And of course, it's not new, the knowledge, because the knowledge is already something that is well treated on the web and in many textbooks, etc. But the presentation that I am delivering here is simplified. So I just wanted to be very technical without giving too much room to heavy mathematical developments. So it's my interpretation. It's not a cut and paste from somewhere. So if you think that something is not clear and you see some mistakes, it may be because it's the first time that I'm lecturing it, the first time that students have a look of it. So if you see something that is, as I said, maybe improved, just let me know, okay? I really rely on your support. Let me see if I have some chalk, because, yeah, a lot. Okay, so mathematical structure of models, this is what we are talking about today. This is what we need to understand. We need to understand in order to understand, as I said, what we are representing, what we are not, and related uncertainty. We already talked about uncertainty, but we talked with a narrative approach. If we learn what is the mathematical structure, even in a very simplified form, we can better understand uncertainties and models. And as I said, we need to understand what models do, because we can't apply models without knowing what they do, because otherwise we expose ourselves to mistakes, responsibilities, and, we can't rely blindly on artificial intelligence models, whatever you call them. Okay, we need our human mediation, and the human mediation, of course, presupposes that we know the mathematical structure. So indeed, we already said that Earth system models in general, including climate models, but also hydrological models, also ecosystem models, are mathematical representation of the dynamics of the involved processes. Okay, and we know that the structure may be very simplified or may be more detailed and more complicated. We know that they can be deterministic, they can be stochastic. Stochastic means that there is some randomness, okay? And basically these models are tasked with a very difficult challenge, that is to represent processes that are highly heterogeneous. Heterogeneous means that are variable in space. Think of rainfall, think of clouds. They are extremely heterogeneous. So in one spot, you don't have any cloud. In the subsequent one, you have clouds. And these processes are typically highly varying in time. So there is spatial and temporal variability. So it is a challenge. You understand that to model a process that is smoothly changing in space and time, it's easier than modeling a process that is rapidly changing in space, which means that it's heterogeneous, highly heterogeneous, and time, which means that it's heavily time varying. So these models are charged with a very difficult task. And how they are composed? They are composed by a set of equations. Mathematical models are systems of equations. Very simply, we know what are mathematical systems of equations from the secondary school. So mathematical models are nothing more than that. And basically, how many equations do we need? It depends on the process, but in general, we need at least a number of equations that is equal with respect to the number of unknowns, as we know. If we have two unknowns, we need to use two equations in a system. Three unknowns, three equations, at least. We may have some cases with redundant equations, but let's take the rule that we have to estimate the number of unknowns and then an equivalent number of equations. Now, what are our unknowns? Just 1 second, because I have to admit persons. What are our unknowns? There is a very simple answer to this question. Our unknowns are the variables to be predicted. Okay, do we need to predict future temperature? Our unknown is temperature. And can you please close the door? Thank you very much. Yeah, don't leave it open. And do we need to predict rainfall? The unknown is rainfall. Temperature may be unknown in several places, and therefore we have more than one unknown. It's only a variable type, temperature, but if I need to predict the temperature in 10 locations, I have 10 unknowns. Okay. However, it's not so simple. I may have more unknowns with respect to the variables that I have to predict. I may have more unknowns with respect to the number of variables that I need to predict. And let me make an example. I think I already, I'm not sure, but maybe I already introduced this example to you. Let's suppose that my prediction refers to river flow in a location, perhaps under a bridge. If I want to predict the river flow depends on what? Depends on the input data, which is in general precipitation, upstream precipitation, rainfall, snow, okay? Input data generally are known. I need to know input data. Otherwise, if I don't know the input data, I can't make any model. But the river flow also depends on the catchment storage, on the upstream storage. I didn't define what is a catchment yet. So if I want to predict the river flow in a river, I need to know, because the river flow depends on it, I need to know the upstream storage, water storage. Because you understand, if you have precipitation over a river, and then part of the water is stored upstream, you don't have any river flow downstream. If you don't have storage, then you have a situation where you have precipitation and you have river flow. But storage is something that I need to know. Storage is not a variable to be predicted. I may be not interested in storage, but I need to know storage, because if I want to predict the river flow, I also need storage. And what is storage? Is a variable that describes the state of the system. The system is the river flow. The system is the river, sorry. The unknown to be predicted is the river flow. The system is the river. Storage is a variable, it's an unknown that describes the state of the system. These variables that are not output variable, are not variable to be predicted, but are variable that describe the state of the system, which I need to know in order to make my prediction, are called state variables. Okay, and there is a link in my website, or a box better, which describes the state variables, and there is also a link to Wikipedia. If you look at the link here, there is a description, state variable. By the way, I open a parenthesis. In this Wikipedia article, there is a note. This article needs additional citation for verification. Pay attention when you browse the web, and in particular Wikipedia, to these warnings. You know that Wikipedia is a community encyclopedia. It's made by people that work on it for free. So you can create your own Wikipedia page, for instance, not your personal Wikipedia page. But if you want to create a Wikipedia page on something that is still missing there, you can do it. It's open. And of course, before publishing, it is reviewed by other people that work for free. And if they have some doubt, they may place a warning. And when you see warnings, be careful of that, because it means that somebody raised concerns. Being a free resource, sometimes when they deal with controversial items, also the warnings may be originated by controversy, and therefore it is anyway useful to know that for certain issues there are controversies open. And the moral of the story is when you use the web and free resources, you have to pay attention to these warnings, okay? In this case, this is not controversial, and it says that it needs additional citations. It's not a big issue, okay? Additional citation. Of course, they want citations in order to be able to verify the information and to verify the reliability of the information. And it's not a big issue anyway, okay? Also because I think that in our case, we don't really need to stick on what's written here. The important thing is that we get the concept. Okay, so now we understand that we may need additional variables to describe additional variables, and therefore the number of unknowns increases. So my unknowns are output variables, let's call in this way the variables to be predicted, plus state variables, and you count them. If you have 10 unknowns, you need 10 equations. And now the next question is, what kind of equations can I use? Okay, we are talking, this is a very nice question, by the way. What kind of equation? Because this is equivalent to asking ourselves the question, what kind of model should I use? Okay. Of course, these equations must relate the unknowns between them. If I introduce an equation where I don't see any unknown, it's useless. Okay, so at least in any equation of the model, I must see one unknown, at least. You may decide to use purely empirical equations. Okay, like for instance, let me see. For instance, in the case of river flow, I make the example of river flow, but I could say temperature, I could say whatever. Let's see. I have to be careful because the white chalk is very short, but I don't have the names. So let's suppose that I indicate the river flow with Qt. Now, before moving forward with the blackboard, let me change the camera. Okay. And let me see if the blackboard, yes, it is visible, perfect. Let me call the river flow Qt in a given location, okay? The location is not explicitly mentioned here and not implicitly, but let's suppose, better to say, let's suppose implicitly that we refer to a location, a bridge, for instance. The river flow typically is varying in time. So let's take something that is varying in time in order to make it very general. So I may say, okay, what is, this is my unknown, okay, unknown. And then I said that the river flow depends on precipitation. Let's call it PT, okay? And this is my input, okay? It is one of my inputs. Maybe I may have also more inputs, okay? I said that I may have a dependence on storage. So the unknown I could put here, let me call storage WT. W stands for water. But I may decide when I build my model, given that I need now to select an equation here, I may decide very simply that storage is not an issue. I ignore storage. I assume that river flow doesn't depend on storage. This is, of course, not true, but I may make this assumption, because if I want to make a very simple model, I could simply say that my model is model. Let's suppose that my model is Qt is equivalent to a coefficient k that multiplies PDT, PT. This might be my model. I neglected one unknown, so I have only one unknown, one equation, and the equation is linear. Okay? It's a linear dependence between river flow and precipitation through what? Through a parameter. We call these coefficient parameters. What is a parameter? It's a coefficient that is used in the equation. Typically, it takes a constant value, maybe also varying in time, which doesn't change the shape, the model structure, but it gives some flexibility. So here, this equation is linear. It's a proportionality between river flow and precipitation. It remains linear, whatever is the value of k. But you see that if k increases, I increase also the river flow. So I give the model flexibility to adapt to the real world. And this is the purpose of parameters. As I said, they are coefficients. Typically, they are constant, which don't change the structure of the equation, but make it flexible to adapt to the real world. Because you understand that if I apply the same model to another river, I need to change k. So this is flexibility. The flexibility is the fact that I take the same model, identical, I apply it to different rivers. And of course, I cannot use precisely the same model, because any river is a different context, it's a different reality. So to adapt to the real world, I use parameters to give flexibility. And this is a very simple empirical model. You understand, first of all, what does it mean linearity? Okay. Linearity means that if I make a graph of Qt and with respect to time, let me say Qt with respect to PT. Okay, if I make a graph of Qt with respect to of river flow with respect to precipitation, the graph is a straight line. And in this case, it's passing from 0, so it's a straight line. Okay, and the slope is dictated by k. So if I change k, you see it remains a straight line, but the slope changes. So it doesn't change the structure, but it changes the result. It is flexible. Okay, and this means linearity. Linearity means that a linear relationship between two variables. It means that if I want to write on a graph the relationship between the two variables, it's a straight line. In this case, it is passing from 0, from the origin. It may also not pass from the origin if I included here plus something, an intercept. This means linearity. But actually, I cannot define linearity in this way. Linearity mathematically is defined by two conditions, which I ask you to pay attention to, because they are very important. And the notion of linearity, it doesn't matter what is the degree program you attend. In any case, the notion of linearity, you need to know it. Why? Because Earth system processes are nonlinear. Okay? The relationship between river flow and rainfall is absolutely nonlinear. Linearity is a useful approximation, but you have to understand what are the limitations. And in order to understand the limitations, you need to understand linearity. I want to give you another example. We wish climate was linear. For instance, think of global warming. We wish that the increase of temperature is a linear function of CO2 emissions. We wish that because we would be much more relaxed. I mean, I am not concerned by a graph like this. I am much concerned by a graph which may be, think of temperature, T, and this is CO2, okay? CO2 emissions, CO2 concentration, whatever. Think of a situation where I have something constant, and then start increasing, and then you get a tipping point like this. This is non-linear, you see, because even if you have here maybe a straight line, here you may have a straight line, here you may have another straight line. It's not a problem. So you don't need an exponential function. You may have another straight line here. So this is piecewise linear. It's made by chunks of linear relationship, but the composition is non-linear. And I am much concerned because this is a tipping point, you understand? I am much concerned that if I get to a concentration of CO2 at a certain level, temperature may jump suddenly to stellar values. This is non-linearity. Threshold effect, tipping point, this is non-linearity. So we wish that climate, Earth system was linear. It would be easy to predict, you know, a relationship like this. It allows a very easy prediction, very easy model. So the moral of the story, you have to recognize what linearity means, because also in the media, you listen very often people saying, climate is not linear, this is a problem. And you have to understand what it means. It means that you may have unpredictable effect. And you need more complicated models to make this prediction. So what is linearity in mathematical terms? I'm not sure linearity is introduced in this lecture, maybe later on. There is the introduction to linearity later on. I anticipate it. And it's you have two conditions that must be ensured to make a function f linear. Okay, so linearity of f. Linearity means that a function f of a times x is equal to a function of x. This is the first condition, one. Okay, it means that if you have a function of a variable x that is multiplied by a constant a, maybe a parameter, you can also express it in this way. Okay, and the second is the additive property. F x plus y is equal to fx plus fy. This is the superposition principle that means that if you have two drivers over a process, the result of the two drivers is given by the sum of the individual results of each driver. And this is also something that is absolutely not true in Earth system processes. Okay. If you have two forcings, the result of the composition of the two forcings is not the sum of the individual results of each forcing. So I may assume linearity here, and the model is very simple. This is clearly empirical, okay? Clearly empirical. Okay. But if I'm not happy with this model, I may try to be more detailed, more precise. So let me present to you another possible solution. Let's suppose that I say, okay, now this is not really useful because it's too much uncertain. We understand it's linear, and besides being linear, I ignore the storage. And if I think at the process, river flow, depending on precipitation, it's not a good move to ignore the dependence on storage. And so I realized that uncertainty increases a lot. Okay. So for instance, imagine that during the river you have a dam. Upstream, you have a dam, which means storage. So if you ignore storage, you ignore the effect of the dam. Why? We know that dams placed over the river have a huge impact. Also some benefits, but some negative impacts, also some benefits because they can store water. So I realize clearly that this assumption that I made, okay, may be good for the roof of an house. Okay, so if you want to compute what is the river flow that comes from the roof of an house, this may be a good assumption because the roof doesn't store much water. It's very steep. It's absolutely impervious, impermeable. So there is no storage. Okay, you have just a little bit of storage because you have a film of water flowing over the roof, but actually it's very reduced. So it may be good for a roof, but not for a river. So I may say, okay, I really want to remove this assumption and I want to compute also the storage. So I need a second equation. I need to change my setting. So let me cancel this now. Okay, cancel this because we decided to reject it. So I cancel it. Let me also cancel the definition of linearity because I think you got it. Okay. And let me take another opportunity. So another way, another setting, as I said. So what could I do here? I need two equations because I have two unknowns. And but besides thinking at purely to mathematics, what could I do? What is the concept that may drive me to set up this model? Okay, I could also take some empirical approach, but let us take another kind of approach. Try to imagine how the system works and build the mathematics that fits the system. So how does it work, the system? Of course, I have precipitation over the river, and I know that there is some storage. The river is storing some water. I don't know how much, but there is some water stored. And then there is a release of water in terms of river flow. So I may assimilate the river to a tank that, and you have a picture in my website, a tank that takes precipitation, stores stores some water, and this is my storage. And I move so you can see it. And then from here, I have my river flow Qt. You see that this is a different approach. I'm trying to understand how the river works. And now my target is to build a model that, to build a mathematical structure that reproduces my thinking. You understand that this is already looking at the dynamics benefiting from my preliminary understanding. Okay. Now, what I can do within a tank like this is to write a mass balance. It's very easy. Okay. What I could say is that rainfall minus, precipitation minus river flow, it's equivalent to what? To storage, increase in storage or decrease in storage. If I have more precipitation than river flow, it means that in this tank, I get more input than output, so the storage increases. Conversely, if I have more river flow than precipitation, the storage decreases. So here I can write the change in storage. It's a derivative. It's a derivative. Mass balance, yeah. Conservation of mass or mass balance. The question was to repeat what is the condition that I am imposing here. It's a mass balance. Mass of what? Water. It's conservation of mass. So this equation that I wrote here, you can call it a mass balance equation. Mass balance. You can call it conservation of mass. Conservation of mass or mass conservation. It's also called continuity equation in some textbook. Continuity equation. Why continuity? You understand why? Because it's a balance, so you make sure that there is a continuity between precipitation and output. And in general, you can call it a conservation law. And there are several considerations that we need to make on what I just wrote here. On this mass balance equation, conservation of mass equation, continuity equation, conservation law. There are several considerations. First of all, I think that you heard the term conservation law several times, and this is the classical equation that we use to build Earth system models. So this is what I wanted to convey to you today. An essential basis for Earth system models is conservation law. Why? Because these processes that occur in the Earth system, very often they indeed satisfy conservation of mass, conservation of heat, conservation of energy, conservation of momentum, which means it's a particular form of conservation of energy. I am simplifying, okay? So basically these processes satisfy, I repeat, these requirements, conservation of mass. Think of the water cycle and think of the mass of water over the Earth is conserved. You don't destroy water. The amount of water over Earth is the same from the prehistory to today. So clearly, if I want to describe the water cycle, this is something that I have to impose. I can describe the water cycle in any way I wish, but I have to impose conservation of mass. And also conservation of energy applies. And you know this because you studied physics. And how do you study the motion of a rigid body or the motion of fluid? By imposing conservation of energy or conservation of momentum. Okay, momentum is a particular, okay, momentum is a vector, energy is a scalar, but the concept is the same. Okay, conservation of energy, let's say, to simplify things. So this is indeed a conservation law. And I got it in a very simplified way, basing on my intuition. I thought of this tank, and I didn't think of a conservation law. I just, based on my reasoning, my understanding, and what I impose there, actually, it's a conservation law. And there is a second consideration I want to make here. You see a derivative. First, don't be concerned by derivative and integrals. Derivative and integrals, traditionally, they are hated by students, and I was really hated them, really. I was very scared when I heard the word derivative integral, but actually, a derivative is just a difference. It's the simplest operation that we can make. And an integral is a sum. So you learn how to compute a sum. It's the first operation that you learn at the primary school. So the integral, the concept of the integral or a derivative is extremely simple. It's the computation that sometimes is difficult. It's a practical computation, especially if we want to make an analytical computation. Computing analytically an integral is a challenge. Okay, but sorry, today we have the PC. The PC can transform the integral into a sum. We don't need the analytical computation anymore. So you don't have absolutely to be concerned. You see, the derivative is just a difference. It's just a difference. And you understand why this is actually a differential equation, because you have a derivative. So once that you get one derivative into an equation, you get a differential equation. So you understand why Earth system models are governed by differential equations. Because when I want to describe the storage, when I want to describe a change in the variable rather than the variable itself, I need a differential equation. So conservation laws, why they are differential equation? Because they need to describe storage. If you remember, the previous equation that was written here was not differential because I neglected the storage. But when I want to consider the storage in conservation laws, I need a differential equation, which is not a problem. Okay, there is actually a complication with the differential equation, that the differential equation, if I am interested in describing W, the differential equation written in this way doesn't allow me to describe W. It only allows me to describe the changes in W. Okay, let's suppose that here I know PT and QT, and my purpose is computing W. I cannot compute W with this equation because I can only compute the change. So in order to compute W, I need effectively to compute an integral, which is fine. It's a sum. It's a sum. However, it's not just enough to compute the sum here, because the sum of the changes, okay? Because let's suppose that I compute W1, the first change of W, the second change of W, the third change of W along time. If I sum them, I don't get the value of W, I get the sum of the changes. If I want to get the value of W, I need a starting point, an initial value of W, and then I sum the initial value. So let's W0 here, W0 plus W1 minus W0. Okay, and this is the first change of W, plus W2 minus W1, plus, etc. So if I just take the sum of the changes, I don't get the value of W. I need to know also W0. And what is W0? It's the initial condition. Initial condition. So these terms that apparently look very complicated, they are very simple if you think of the derivative as a difference and the integral as a sum. Okay, so what is our conclusion in this first hour? Candidate equations for Earth system models are conservation laws. And conservation laws are often expressed in differential form, and this is why Earth system models are composed by a set of differential equations. And to resolve this differential equation, to apply Earth system models, we may need an initial condition. And we may also need boundary conditions, but let's forget about because if the integral is computed in space, I cannot say initial condition. Initial only refers to time. In space, we use the term boundary condition. And now the panorama is clear. So this is what we reached during this first hour, okay? On the other hand, we are not done with this model because we have two unknowns, only one equation. So I need a second equation. Let me gain some space in the blackboard. So this is conservation of mass, we said. I may take another conservation law because you see here, I have only one equation, two unknowns. Two unknowns. Two unknowns. So I need a second equation which can give to me either explicitly the value of W, so this is no more an unknown, or a second equation may be a relationship between another relationship between Qt and W. If I get another relationship relating the two unknowns, that's fine. And I said that conservation laws are ideal candidates. I used conservation of mass. Another possibility could be conservation of energy. Conservation of energy. Because I understand that the relationship between the storage and the river flow is governed by conservation of energy. Storage means potential energy. River flow means kinetic energy. Because river flow is something that is moving. The storage is something that is basically static. So storage means potential energy. Think of a reservoir, a dam, an artificial reservoir. We use it to make hydropower. Why? Because it's energy, it's potential energy. Water stored in a reservoir, it's potential energy. Water flowing into a river, it's mainly kinetic energy, because you don't have a huge amount of water into the river stored, but you have water running, and the movement is energy. In fact, sometimes we also generate hydropower by placing a turbine into the river. And the flow, the continuous flow, moves the turbine and produces energy. It's kinetic energy that is transformed in electricity. So it's a conservation of energy. The more storage I have, and the more the river flow. So I could write easily a conservation of energy for a tank, but I don't want to make things complicated now, okay? Because it requires some basic notions of hydraulics, which I don't want to introduce now. There is another solution proposed by the literature and used by earth scientists for solving this problem. And the solution is, at this stage, to simply write a linear relationship like Wt is equal to Qt, K, a coefficient K, times Qt. A linear relationship, okay? A linear relationship between what? Between storage and river flow. And then I got my system of equations. I got my model. Two equations, two unknowns, conservation of mass here, an empirical equation here, which must be equivalent to conservation of energy. Must be, okay, because conservation of energy applies. And when I assume a linear relationship between storage and Q, I already explained to you, it's a conservation of energy. So this is equivalent to conservation of energy, but actually I got it through a linear model. That's it. This is an example of a very simple Earth system model. It's not an example of a climate model. I will also give to you an example of a climate model. But to give you an anticipation, to describe the global temperature, you may write conservation of heat. Conservation of heat. You put the solar irradiance in as an input, and the output is global temperature. You don't have a tank in that case. The tank is substituted by the Earth system. So you get solar irradiance into the Earth system, and you compute the temperature. This is conservation of heat. Very simple. It's an example of climate model. I think this one is more understandable. The tank, this is also called a tank model, a bucket model. You can use this kind of model also to describe other processes, not only river flow. Actually, if you want to describe it, if you want to use it for describing river flow, there is something more that I should say. It's not finished because I didn't get an explicit representation from here of Qt. You understand that our target is getting a prediction of Qt, an explicit function for Qt, and here it's not there yet. So I need to make some development here. But let's forget for now. We will make these developments later. Because our final target is to get an explicit representation of Qt. I'm not interested in WT. You understand that here the way to move forward is to make a substitution. I can substitute WT here. So derivative of not WT, but derivative of K Qt. And then I get an equation with only an unknown, is a differential equation. I need to integrate it, which is easy, but we don't do it now. Okay, any question? You know, when I get the final survey from students, usually when I propose the interim survey, students don't write comments. They just reply to the answer. For the final survey, usually I beg that you write comments, and then every year I get, okay, this course is the first year that I teach climate, the second year that I teach climate change adaptation. But in the past, I was teaching a similar one. It was called the Sustainable Design of Water Resource Systems, and it was more on water cycle than on climate. And now it's more on climate than the water cycle. But anyway, the kind of comment that I get at the end, there are some students that say this is too tough, too math, and other students that say this is too simple. Because you are very diverse, the audience is very diverse, which is nice, it's very nice. After the start of international programs, we got an increase of diversity in the audience of the students. Because up to 15 years ago, mainly the students, 90% of the students in a master took their bachelor in Bologna. So we were fully aware of the background, everything. And now it's more diverse, which I think it's nicer. On the other hand, it looks like walking over a very small wire, let's say, and you have to stay in equilibrium. So I try to stay in equilibrium, and when I introduce math models, I try to simplify things. But last year, indeed, I got at least 3-4 students that said I would have preferred more modeling. And so now I am trying to make some more modeling. So no questions? Okay, now I need, if you look at the website, there is indeed this example here. It's not developed as I did in the Blackboard because the development is more general, okay? And it's more general and refers to a generic process, not to a specific case like this. I think the specific case allows you to get the meaning, to grasp the concept. Now let's make it more formal and more general. So let me gain room in the Blackboard. And let's start from our understanding that conservation laws are indeed an extremely interesting tool for us. So let's now try to understand more on conservation laws in general. Okay, conservation laws can be applied to a generic volume. And as you can see on the screen, the sketch, you have here a generic volume. And the previous example was a tank, which is a specific volume. Okay, my volume of analysis was the tank. Let's now refer to a generic volume of whatever shape, a volume capital V, which is delimited by a contour surface S, which we may split in small pieces, infinitesimal size, ds, and let's assume that we have a normal vector to each piece, ds, which I indicate with the letter n, lowercase n, and the vector is pointing outward by convention, just by convention, okay? And this is our volume where we apply a conservation equation. And this is called a control volume in mathematical terminology. And we call this volume an inertial frame of reference. What does it mean, inertial? It means that it can be fixed in space or can be moving with no acceleration. This is an inertial frame of reference. Typically, in such a frame of reference, if you don't have acceleration, you can study it in the same way as it was fixed. Okay, you just have to change the system of reference from Eulerian to Lagrangian, but I don't really need to stick on these details. So you don't need to know what is an inertial frame of reference. You need to know what is a control volume, because this is basically essential to understand the conservation law. The conservation law is applied to this volume. It's a control volume. And it's just enough if you know that it can be fixed or it can move. It doesn't matter. The only thing that matters is no acceleration. Because if there is acceleration, you understand that it's like forcings, okay? For the first of the Newton's laws, if you have acceleration, you have a forcing. And so if you don't have acceleration, it doesn't make any difference. Okay, it's a control volume, and let us consider the conservation of an arbitrary property, which is indicated here with the symbol P. Okay, phi or P in this way. So here in the web page, I couldn't solve this problem. In the text, phi is indicated in this way, text. In the equations, it's indicated in this way. It's the same thing, equations. I will try to solve this problem. Sorry for that. Okay, and it is relatively easy, so I will fix it. For now, it's not fixed. Okay, it's relatively easy to use this one in the text. Just for those of you who like this web publishing, probably nobody. In the text, it's written in HTML codes, and while the equations are written in LaTeX. You probably don't know LaTeX, or you may know it. And my suggestion, if you don't know LaTeX, try to browse the web, understand what it is. It's a word processor. It's not as user-friendly as Word, but the quality is superb. It's super. And books are published in LaTeX. And when I publish scientific papers, many publishing houses ask to send the LaTeX file, because the quality, as I said, is superb. And if you look also at the equations in here, you see the quality of these equations, it's super. And so I don't want to, you don't need to know web publishing, absolutely. Okay, it's, of course, if you know it, if you build your own website when you are a professional, or when you are also just graduated, if you build your own website where there is a CV, and it's useful. But there are several ways of building a website without knowing the details of web publishing. So you don't really need to learn it. But LaTeX, I think it's a plus. And if you put in your CV, expert LaTeX or LaTeX user, I think somebody will say, interesting. And it's really not difficult. Absolutely. There are online services today because once it was a problem also to compile, to put the software in our own PC. But now I work online with LaTeX, and it's very easy. Okay, so as I said, this quantity, it's an arbitrary property of which we want to write the conservation law within the volume V, okay? And let's indicate with the symbol V the density of capital Phi. This is lowercase phi in Greek letters, and this is capital Phi. So lowercase phi is the density, okay? And the density in general depends on the position within the volume. We can assume that it's constant. If it is constant, like for instance, when you refer to the density of water, we assume that it's constant because it's incompressible. For many practical applications, water can be assumed to be incompressible, so the density is constant. But in general, this density can be varying in space. Within the volume can vary, okay? And because it is varying, I should indicate here the dependence on space, x, y, z, and also time. So basically, we are talking of a system that is changing in time. So, of course, phi is changing in time, and the density is also changing in time, but it's also changing in space. So to be very formal, to be rigorous, I should indicate for any time that I mention capital Phi, I should indicate the dependence on time. Anytime that I mention lowercase phi, I should indicate the dependence on space and time. What we do here to simplify notation is that we omit these dependencies, but this must be clear to you that this one is changing in time, capital Phi, and rigorously speaking, it may also change in space because the volume is located in space. So these dependencies, I am omitting them because otherwise the notation becomes very heavy, and I think it is useless. But keep in mind that we are talking of processes that are heterogeneous and changing in time. So changing in space and time, always. Unless we say it's constant, because some properties may be constant. Just keep in mind that. So this is an arbitrary property of density phi, and then we have other symbols. Let's see here. The property can be whatever, as I said, energy, mass, heat, whatever. No, in general, capital phi is changing in time. I'm not highlighting the dependence here because it makes the notation it, but in general, it is changing in time. Okay? Energy is time changing. Is it clear? It change in time? Sorry, I didn't understand the question. It's a fixed term, you said. What do you mean by fixed term?
Always have to expect
Yeah,
it.
always you have to expect that it's changing in time. Yes, it's fixed term. I understand your meaning now. Okay, perfect. Any other question? I want to define also the other symbols. And another symbol is, let me see. Okay, of course, capital phi is expressed in the units of the property. If it is energy, the units of energy. If it is mass, the unit of mass. And the density is unit of property per unit volume, of course. Let's always keep in mind the units. And now, how can I describe, how can be the total quantity, the total amount of capital phi change in the volume? So let's refer to this first equation, left-hand side. This is the change in time of capital phi. Why capital phi? Because it's not explicitly indicated here. Because what I'm computing here is density times volume, which is integrated. Why it is integrated? It is summed over the volume. Why it is summed? Because I want to admit that for any individual small piece of volume dV, I may have a different density. Density may be varying in space, and therefore I compute the integral. So this integral, which is density times volume, is nothing else than the computation of the total amount of capital phi within the volume. And I want to describe the change in time. Is it clear? What is the left-hand side? Change in time of capital phi. Capital phi expressed as the product of density times the volume, and the integral is just necessary because I want to split the volume in very small blobs, because I want to allow the density to vary in space. But the dependence is omitted here because I wanted to simplify. Okay, so how can the change occur? The change in time of the property, capital phi within the volume. How can it occur? Okay, there are three possible contributions. First of all, it can change for the presence of a source term inside the volume. The source term is H. Okay. It's computed like an integral, again, because I want to take into account the variability of H within the volume. So what is the unit of H? Is quantity, so capital phi, per unit time and unit volume. It's the production. H is the production, the internal production of capital phi per unit time and unit volume. This is a source term. Everything is clear? Perfect. And the source term, in some of the cases, can be neglected. This is very general. And then when you go to specific applications, you can omit some of these addendums. Now, capital phi can change also for transport, meaning that you have part of the volume that is moving out or in through S, through the contour. you have transport, okay? So for instance, think of water that is moving inside the volume, is entering the volume and moving out of the volume. So this movement with velocity v means a transfer of mass. If our capital Phi is mass, we have water moving from transport. But in general, this is the transport term. What is lowercase v? It's the velocity of the transport. It's the component of the velocity of the transport along the normal direction to S, to the contour S, okay? So this is the velocity of the transport, lowercase v. Velocity of the transport is the component of the velocity normal along n. Along n there, okay? And then you compute the density, and this is computed over the whole contour S. And this is, again, the flux, we call it flux of capital Phi through S due to transport. Finally, we have a third component, which is a movement of the quantity capital Phi through S that occurs even without transport. And let's, for instance, make the example see, I think it is mentioned here, heat conduction. Okay, so even if heat may go out and in the volume V, even without transport, for conduction. And then if we have also air that is moving, so there is transport, there is a change of heat. And what is F here? F is the flux, I want to use the same word, the flux of capital Phi in absence of fluid transport. We call it F, flux of capital Phi through S in absence of fluid transport, and is expressed in terms of unit of capital Phi per unit time and unit surface. So this is the general formulation of a conservation law. That's it. And this is the same equation that I applied before in the tank, where I removed the source term, I removed the component capital F, and I considered only the flux due to transport. So what I wrote was, if you will remember, this is the T of W, which is precisely this left-hand side. And I wrote precipitation minus river flow. It's this integral here. And the other two were neglected. This is the general form. This is also what is called, it's a simplified form of what is called the Reynolds transport theorem, which you may have heard of. You don't need to learn anything of the Reynolds transport theorem. I just want you to get a full perspective of what is a conservation law and what are the general and different formulations that a conservation law may be presented. There are some textbooks that start from the Reynolds transport theorem, is mathematically a bit heavier than what I presented, and they come to a similar conclusion. Okay, actually, I can't say that this is a Reynolds transport theorem because it's simplified. So what I wrote in my website, if you scroll down, I think I wrote something. Okay, equation 1 is a simplified form of Reynolds transport theorem. Okay. Now, if you are a non-engineering student, what kind of question could you find it in the quiz or in the oral. Okay, you don't need to learn this relationship in this form. Okay. If you are an engineering student, please take into account that when we talk about Earth system models, this is the basis. So make an effort to learn it. I'm not saying that you don't pass the exam if you don't remember this, but I am saying that if you want to pass brilliantly the exam, you should learn this. And I dedicated a lot of time with this purpose. And you may find, if you are a non-engineering student, you may find questions in the quiz of what is a conservation law, and you may have the choice between three narrative forms of what is a conservation law. You may find a question on linear equations, even if you are a non-engineering student. And you may also find a question like why a linear relationship is reassuring when dealing with Earth system models. And you have 3, 4, 5 choices, and you have to select the correct one. And that's it. But you don't really need to learn this if you are a non-engineering student. Another thing for non-engineering students, for everybody, sorry. Okay, here there is a formulation with, there is no source term and only fluid transport. Okay, this is a simplification. And this is the explanation of what I just mentioned before. And that for the tank case, the above equation, equation 1, leads to the very simplified form, precipitation minus river flow. And here there is a box, application in continuum mechanics. It's just for your information. You don't need to learn this. I just wanted to give you these additional developments because you may see the conservation equations presented in this way. Look at equation 6, this one, with f equals 0 and h equals 0. So you may find quite often the conservation equation expressed in equation 6 or equation 7 with the use of the divergence of the nabla operator, which is divergence, which I think you remember better than me what is. But in any case, you don't need to learn this for preparing your exam. It's just if you want to get additional details. Okay, a couple of things more I want to say before we make the break. It's just give me 1 second. Okay, so the conservation law here, actually, when you pass to the specific form of the conservation law for a given process, like the tank example, assumes a completely different structure, because it depends. You of course have to describe here additional variables like velocity. In this case, here you have velocity, and in the tank case there was the volume. So there are additional variables that need to be described, and there are specific formulations to describe these variables. Like for the tank case, there was a specific empirical formulation for describing the storage, which may contain parameters. These parameters, I didn't discuss of this, need to be fixed, estimated, and we will talk later about this. Okay, later on we will talk about specific models, which we rely on a conservation of mass and energy typically, and then I will also discuss estimation of parameters. Okay, let me just go down. Okay, any questions so far? Okay, so when we talk about climate models, they are, yeah, this is what I wanted to say. Models can include, like climate models in some cases, can include equations that are not conservation laws. So we are not strictly committed to include conservation laws and only conservation laws. I would say that any Earth system model should contain in some form a conservation law, like conservation of mass, conservation of energy, but we can also include equations that are not conservation laws. For instance, to give you an example, there are models that include an economic component or a demographic component. They include socio-economic components. The socio-economic components not necessarily are conservation laws. So in economics, you may resort to some conservation laws, like, for instance, the conservation of the capital, but there are also laws used in economics that are absolutely not conservational. And so you may have additional equations. Typically, climate models include only conservation laws, unless they include a component based on evolutionary principles. Evolutionary principles are principles that are different from conservation laws. And evolutionary principles may be used in modeling ecosystems. So basically, if you want to model an ecosystem, an evolutionary principle may be used to select what is the species that is surviving and the species that is dying. And this is not a conservation law. It's an evolutionary principle, it's another thing. And there are also theory postulating that also some other processes like the water cycle can be modeled by using only evolutionary principle, or let's say should include some evolutionary principle, because there are modern views that admit that the water cycle is also regulated by ecosystems, by an ecologic component, a life component. So when you have a live component in your models, evolutionary principles are often called into play. So you may have other set of equations. Typically, current climate models don't apply these equations. They only apply the equation of physics. They come from atmospheric physics, so they apply conservation laws. These conservation laws, this is what I wanted to say and I was forgetting, these conservation laws are applied on a small blob, a small volume like this one. So if you want to apply to the entire globe this kind of approach, you can't use, or I mean, it's a very coarse approximation, a very rough approximation if you consider the entire globe like your control volume. Because when you compute a conservation law over the control volume, you lose the information on internal variability. You see that there is computation of integrals here. Computation of integrals, which means that at the end of the story, you get, as a result, the change of your property in the volume, but you lose information on internal variability. And so the conclusion is easy. If you consider the whole Earth as a unique control volume, you lose any information on the variability of climate over the Earth. So it can be suitable if you want to model the global temperature. Indeed, global temperature is a number, but you doesn't give any information on the variability over the Earth. So if you want to model global temperature, that can be fine. The control volume is the Earth system. But if you want to describe heterogeneity, and usually, with climate, you want to describe it, basically, you can't use the whole Earth as a control volume. So what you have to do is to use something like, 1 second, I take another web page and you have to use 1 second, climate models. You have to use a representation like this one. Sorry. Okay. So your globe is divided. Sorry, it's not high definition. Your globe is divided into a grid, into a composition of control volumes. Is split with a myriad of control volumes, and then you need to apply the conservation laws to each one of them, with the complication, with the additional complication that when you want to compute the flux due to transport or the flux due to convection through the surface S of each one of these millions, the flux depends on the neighboring control volumes. So you can't compute the results individually. You need to put together a system of millions of equations. You understand why global models, global climate models can be run only by a few computational centers in the world. Okay, they cannot be run over a personal computer unless you simplify. You may use a grid with only few pieces, but then you lose the information on spatial variability. So you understand what is the complication in our case. The conservation law in itself is not so much complicated. But when you have to apply over a grid to the entire globe and where everything is connected, you understand the complication. Okay. So I think we can close here, and we can make the break, and then we move forward from 11. Thank you.
Hey, Professor, I
Yeah.
have a question.
Yeah.
What was the difference?
Okay. 1 second. Good. Okay. Any question? No questions. Okay. I think with this addition, the third link, the lecture on the Earth system, is completed. Now, the next hour will be dedicated to more narrative discussion. So no math anymore for today. And we refer to the link, the climate change problem, which is given here. And I have a PowerPoint. 1 second. Here it is. Okay, first, in this lecture here, you will see, especially in the web version on the site, not in the PowerPoint, also to some extent in the PowerPoint, you will see some repetition with respect to the previous lecture. Of course, I will not repeat things in my lecturing. What you will find in the web page, in the lecture note, is some repetition, in particular a couple of figures. Please be patient because the repetition is caused by the fact that these are lectures that are delivered to different students of different degree programs. So when I put them together, of course, the sequence of the lecture is different. So in your case, there is some repetition, which I will skip in my lecturing. So I will not repeat things in person, but you will find the repetition in the notes. Of course, when you study, you recognize the repetitions and you understand why, okay? Now, I want to speak a little bit more about why we are so interested in the climate change, why there is some controversy, why there are still open research questions. This is a follow-up of the first introduction that I made. So in some of the cases, there will be also some overlap with the introduction. So I will skip the slides where there is this overlap. But definitely here, I want to give perspective that is more detailed. The introduction was very general. And I was also want here at the end of the lecture, which I'm not sure we will have time today to discuss, I want to discuss with you the data that we have, the data that we use to make to set up climate models and climate change models, because you already understood that any model needs input data. So in the case of the tank, it was precipitation, but in general, there are several more inputs. And unfortunately, I already mentioned that we don't have long records of climate. So we need, in a way, to find the solution to make sure that we have enough data to analyze. Okay, so let me just start by recalling one thing. Climate change is strictly related to sustainability. We mentioned this in the introduction. And the awareness of sustainability is relatively recent, and the first concerns about sustainability emerged after the Second World War and around 1960, end of the 60s, after the economic boom. The economic boom now is known to young generation for the term boomer. Okay, so I think I'm not sure I am a boomer. I think I am already in the next generation. But anyway, you know that there was an economic boom around the 60s, and this is why after the development, after the economic boom, we had the concerns related to sustainability. And I think it is, here you see some examples, but I don't think we need to spend time on this. Sustainability also entails climate change because, of course, climate change is supposed to make sustainability even more challenging because of the changing conditions. And, if on the one hand, the Earth always changed and the climate of the Earth always changed, it's also true that this is the first time that we experience a climate change within a socioeconomic setting that is unprecedented. And therefore, these changes cause an impact from a socioeconomic point of view that is really concerning, because we are also concerned about the sustainability of the socioeconomic development in its overall setting. So after the economic boom, there was the emergence of the liberalism and globalization, and the globalization brought an illusion of global and indefinite development and spreading of democracy. So liberalism brought this illusion that by stimulating globalization and by stimulating the economic development, we cultivated the illusion that the system could evolve to a self-regulating asset, which we thought that was the basis for exporting democracy at the global level. Actually, after the recent economic crisis and the recent international tensions, and also with the pandemic, we realized that indeed the system is not self-regulating. And today there is a lot of concern related to international tensions, and the concern is also related to sustainability. So it's not very clear how the future will evolve to. And climate change is in a way related to these problems. I don't think climate change is a priority driver of these tensions, but of course it has a role. And I don't think it is a priority driver because I don't think that if you look at the international situation now, I don't think the reason is only climate change. It's not a priority. But on the other hand, of course, it has a role because it's moving also, it's stimulating migrations, and it's stimulating a kind of tensions for getting resources. So, and that's it. Now, some examples of unsustainable impacts of societal developments: intensive agriculture, construction of dams, demands for energy, and CO2 concentration. And these are, all these developments are positive because intensive agriculture is essential for ensuring equity, for ensuring food for everybody. And so, it's a positive development. We couldn't do without intensive agriculture. On the other hand, the impact is really massive in terms of water uses, in terms of fertilizers, in terms of groundwater exploitation. Groundwater exploitation is mentioned here only briefly, but it is a reason of concern. I would say that today the concern is a little bit mitigated for groundwater exploitation, but this is really an issue because there are several countries that are relying on groundwater exploitation and use of fossil water heavily. And the use of fossil water means that we don't know how much water is there, because in groundwater we have this problem, and it may seem impossible to you, but we don't have any mean to understand what is the capacity of groundwater reservoirs. So we just use them, we monitor them, meaning that we try to understand whether the level in the wells is decreasing, which is an indicator of the status of the groundwater resources. But really, we don't have an answer to the question, is sustainable the rate of pumping? Is sustainable the use? How much water is there? It's not like a dam, a reservoir. We know how much water is there because we can see it. But on the other hand, for groundwater, we don't have a reply. And it is something that usually water boards don't understand. They say, but how it's possible? I mean, there must be a way to estimate how much water is in a groundwater body. And actually, there is no way to reply to this question. And the replenishment takes a long time. If we use fossil water, it means that it's water that is staying there, has been staying there for thousands of years. We are using this water. It's not clear how long it will take to replenish it. Of course, you may say, if it's fossil water, if water age, which we can know with the analysis of isotopes, if water age is 2,000 years, it means that it will take at least 2,000 years to replenish. This is really not true, because if the reservoir is full, you don't get any water into it. If you empty the reservoir, it may be that relatively quickly the fossil water is replenished, but actually we don't know. We don't know, and this is a big issue. And you understand that there is the concern of global groundwater depletion. And this is something that, in case it turns out that our groundwater exploitation is unsustainable, this has really the potential for triggering wars, large-scale wars. And so all of these questions make the issue of sustainability and climate change really important. And not to speak about CO2 emissions. We will talk about CO2 emissions later, but you are well informed on the debate related to CO2 emissions. And again, dams are beneficial. I couldn't imagine our current socioeconomic setting without dams all over the world. I couldn't imagine how we could survive without energy with the current standards. It's clearly impossible. And I couldn't think of a way, an easy way to live without carbon, without paying an amazing, a very massive social cost. So these developments are all positive. On the other hand, because they are positive, they are difficult to live without. And there is no clear solution up to now on how we could make these uses sustainable. And also there is no clear solution on how to understand if these uses are sustainable. It's not just a matter of political will. Keep in mind that, yeah, of course, we need also the political will, which is in a way conditioned by the consensus of the population. We live in the Western world. There is a prevailing democratic regime, which means that politicians are elected, and of course they are also motivated by reaching consensus. But on the other hand, if reaching consensus is difficult, it's because we don't have a clear solution, and some people would suffer from most of the people would suffer from reduction of intensive agriculture, reduction of energy production, reduction of CO2 emissions. This is why the whole system is in a kind of lock-in situation now, because everybody recognizes that it's a concern, everybody recognizes that we need solutions, but the actions are very limited, very, very limited. And it's a lock-in situation, which is generated by the fact that indeed we need to gain a better knowledge. Okay, so climate change, we already defined weather and climate, so let's forget about it. We already defined what is climate change. There is an issue that, a detail that I want to discuss with you here with this slide. And I take the inspiration from the picture that you see on the right, which is the increase of temperature during the past 120 years, more or less, up to 2007, so last century, 1 century, in several cities. And you see that the trend is different. The trend is different, and in particular, Tokyo is increasing in temperature more than the other cities. Why is that? I move to the next slide. The reason is the heat island effect, which is something that we realized about 30 years ago. And it's the effect given by the internal heating in cities. It's a local effect. On the other hand, we only recently, I would say the past 5 years, recognized that even if this effect is local, it's affecting most of the global population, because most of the global population lives in big cities. And, sometimes we tend to assume that local problems are not relevant at the global level. And indeed, in terms of Earth's surface, big cities occupy like few percent of the global Earth's surface. So at the global level, people tend to say this is not very relevant. On the other hand, when it is something affecting the majority of the population, it becomes global and very relevant. And this is a problem that requires a different approach with respect to global warming. A different approach because it requires also a local approach. And it has been recognized as a severe problem for human health, because not all the people have the possibility to benefit from air conditioning. Air conditioning has downsides anyway, and we know that because we know what is the effect of air conditioning. We don't realize that sometimes when we feel like the weather is warming, the climate is warming, it's a local effect because we mostly live in cities. Of course, there is also an effect outside of the cities, but in the cities is much more relevant. If you look, I go back to the previous slide, and the increase in temperature in Tokyo is like 2.5 degrees, twice than global warming. And in some of the cities, it's more than that. For some cities, they detected an increase of 5 degrees. So you understand, it's really a huge problem. What is the solution? Is greening, because the heat island effect is due to air conditioning, for sure. It's due to the fact that, and this is probably the main effect, it is due to the fact that cities are paved. So the solar irradiance is reflected into the atmosphere of the city instead of being absorbed. And therefore, the solutions that we are trying to adopt are greening solutions, increasing the density of green areas into cities, using green roofs where it's possible, because it's not possible everywhere, using green walls, etc. And so the moral and the concept that I want to deliver to you, try to identify what are the global problems from the local problems. They require a different approach. And local and global in terms of space. I'm using global in terms of space, not in terms of number of people, because in terms of number of people, the heat island effect, as I already told you, is a global problem. But in terms of space, it's a local problem. It's affecting only a small portion of the Earth's surface. So solutions are different, responsibilities are different, and approaches are, of course, different. And let's not to forget the global scale of local problems, okay? Because there is sometimes we tend to assume that these are problems that are not so relevant because they are not global in terms of space. Let's not to forget that in terms of adaptation, here we have a lot to play. While, I mean, at the global scale, it's more difficult and it's more for mitigation, the global scale, mitigation of climate change. For adaptation, here we have a lot to play, a lot to say and a lot to play. And don't forget that there are constraints that are not easy to manage. To modify the urban setting, it's not easy because you understand that once that you paved an area, people are living there. You can't remove houses, you can't remove roads easily. And there is also the fact that cities are part of cultural heritage, and cultural heritage is protected. Especially in Italy, we can't use green roofs. In Bologna, for instance, downtown Bologna within the ring, we cannot use green roofs. We can use green roofs outside here, but not inside the city because it's not part of the cultural heritage, and the cultural heritage is protected. And keep in mind that protecting cultural heritage is not just a matter of tradition. Cultural heritage is recognized to play an essential role for the health of people, for the mental health of people. When you destroy cultural heritage, you create a lot of stress. It's not just a matter of saying, I want tourists, I want to make money from, but can you imagine if somebody decided to remove the Colosseum? The stress for people. It's not easy. Okay, so let's focus now on the forcings because I want to move towards data, okay, to the data that we need. Forcings for climate models means input data. And so the most important is solar irradiance. The Earth system gets energy from the sun. The sun is the only source of energy. You may think, yeah, there are other things like potential energy of water. Yes, but the water cycle is engineered by the solar irradiance, by the solar energy. Without the solar energy, you wouldn't have a water cycle. So the source of energy is energy from the sun. And solar irradiance is defined as the power per unit area. So, and it's a unit area in terms of surface of the Earth received from the sun is measured typically in watts per square meter in the units of the international system. And keep in mind that solar irradiance is not constant in time. And of course, it's not constant in the 24 hours, but it's also not constant in the long term. There is a variability of the solar irradiance that goes beyond the variability of the day and the variability of the seasons. And it's also not constant over the globe, over the Earth. So there are countries getting more solar irradiance and countries getting less solar irradiance, which means that there are countries receiving less energy than other countries. And the most important variability, interannual variability that we know of the solar irradiance is the 11-year sunspot cycle. On the other hand, there are other variabilities which we don't know. And today there is, I don't understand why, there is a kind of attitude to assume that the solar activity is not much varying. Actually, we know that solar activity is varying. We know that sometimes variations are unpredictable, and we know that changes in solar activity have a profound implication in changes in climate. So we still don't know what is the origin of glaciations, for instance, and we still debate whether possibly it has been a decrease, because of glaciations, a decrease in solar irradiance. So it is really something that still we don't understand. I'm not really sure to what extent we will be able to understand more. Of course, observations are a key source of information. On the other hand, keep in mind that there is this uncertainty pending on the solar irradiance, which is one of the main drivers of climate. Of course, now we have measurements. There is a global solar atlas by the World Bank. Let me see if we can open this window. So let me just see. Global Solar Atlas of the World Bank. There are protections, so I can't open. Just 1 second. Here. Okay, global. I just wanted to show you what kind of data you can find there. Atlas Bank. Okay, it's here. Okay, here you have a global map. Let me see. Okay, a global map, I think it refers, I don't understand if it is today's map or season or what. Let me see, map. Okay, anyway, from this website you can get information, and you can recognize, of course, something that we know, like there is more solar irradiance at the equator and the southern hemisphere, and there is less solar irradiance in the north of Europe. And let me see. And I just don't understand whether this is a global map. I mean, I don't understand if it's an average map over the year or if it is referred to a certain season. We don't need to inspect this. I just wanted you to know that this is a forcing that is monitored. So we have measures of the solar irradiance at the present time, but we cannot predict how it will evolve into the future. There is a lot of research activity on this. Space sciences are studied also with the purpose of estimating the income of energy to the Earth system. And then we have greenhouse gases, which are another important forcing for climate models. So what you can see there, and from our world in data, is CO2 emission per capita versus gross domestic product in 2018. And the gross domestic product is on the horizontal axis, and the emissions are on the vertical axis. And what you can see is that there is, a progress that is more or less not much increasing. So CO2 emissions are not much increasing up to a certain threshold of GDP. The graph is non-linear. And if you look at the average, you see that after a certain threshold, you get a sharp increase, meaning that the CO2 emissions are dictated also by socioeconomic development. And the increase is very sharp after a certain threshold. So it is, of course, quite obvious that where you have higher welfare, you get more CO2 emissions. But if you look at the reverse question, would it be possible to have a high welfare with low CO2 emissions? The answer is not so obvious. Of course, if you pay a social cost, reduce the welfare, you reduce the emissions. This is clear, and this is what this graph says. And the question on the possibility, the opportunity to push down this progress is still open. And but on the other hand, the fact that it's non-linear, in a way, it opens a certain hopes, because one may say, okay, let's try to avoid the extreme part of this, if it's possible. Let's study how we can mitigate the exponential part of it. Let's keep the linear increase, and let's try to avoid to pass the threshold. This opens some opportunities. I'm not sure whether this is possible, but this is what I think we need to study, to try to profit, to transform a problem into an opportunity. So when I look at this graph, of course, I say, yeah, this is a big problem. On the other hand, if it was linear, I would say it's almost impossible. I mean, it's a clear law. It's not linear. It's clear that there is a tipping point, so it's possible to avoid this exponential decrease. And okay, with our world in data, you can play with a lot of these graphs, and clearly, I mean, this shows that CO2 emissions are related to socioeconomic development. You may say this is obvious, once again. On the other hand, keep in mind that humans are not the only one emitters. Also, the oceans are emitting a lot of CO2, and therefore, this association between CO2 emissions and human activity is an important indication. Another forcing, aerosols. Aerosols, dust, smoke, are released by human activity, but also by natural phenomena, and they are an important forcing. Usually, aerosols, their net effect is cooling. Okay, and keep in mind that we made an effort and we succeeded to reduce the human emissions of aerosols after 1970, 1980, and we succeeded indeed. And because aerosols, they bring a lot of negative implications, because by only looking at what is written there, you may say, okay, let's increase the concentration of aerosols. There are implications on the human health. So this is why we decided to decrease them. There were implications in terms of size of the ozone hole. You know that our atmosphere is protected by an ozone screen that helps us to get protected from the direct negative effect of solar irradiance. And there is the ozone hole, which in 1980, 1970s was increasing in size, and this was a huge problem because there were concerns for the implications on the human health. So I mean, aerosols, I think we succeeded in reducing the human emissions. Their concentration is reduced, and that's fine. And we don't have to go back to that situation. But on the other hand, let's keep into account that the global effect is cooling, like it happens after volcanic eruptions of a certain size. You may remember, I don't remember the name of the volcano that erupted a few years ago, I think 10 years ago in Iceland. And for a couple of years, we got a decrease of global temperature after that eruption. Okay, and I mean, we succeeded in reducing the aerosols, but it's not as easy to reduce the CO2 concentration. It's more complicated. Aerosols, it was relatively simple. Okay, and clouds have an enormous impact on the Earth's climate, and it's not yet clear whether the increase in temperature at a certain point will self-compensate with the increase in cloud coverage. It's not yet clear. So far, this kind of feedback, of negative feedback, has been very limited, and it's not clear what will happen into the future. In terms of greenhouse gas emissions, this graph here is, again, from our working data. It's extremely important to you, and it's the graph of the emission scenarios that we predict for the future. And I'm sure that you heard a lot of time talking about the business as usual scenario and the Kyoto target scenario. So what is business as usual? It's the scenario of human CO2 emissions. It's emission or concentration, just emissions. It's the global scenario of CO2 emissions that we expect with no policies. This is unlikely. This is overly skeptical, overly pessimist. And of course, there is an uncertainty. The uncertainty, these are predictions obtained by socioeconomic models, nothing to do with Earth system models. They are just, or at least, they are connected to Earth system models, but they have a completely different structure. So these are models based on prediction of socioeconomic developments. Of course, they rely on some assumptions, like absence of relevant and unexpected conflicts at the global level, because of course conflicts increase during the onset of the emissions. Wars increase the emissions dramatically, and then depending on the extension of the war, they may cause a decrease in the emissions because they may cause a recession, an economic recession, and with recession you have a decrease of emissions on average. So basically these models make some assumptions. There are several different models relying on different assumptions, and therefore the simulation gets not really deterministic. There is a set, an ensemble of future prediction. Anyway, they have in common the fact that they assume no climate policies, and this is called the business as usual. This scenario today is considered, as I said, to be overly pessimistic because there are already climate policies in place which have already decreased our emissions. There are some scientists that are convinced that we already reached the top and now we are starting to decrease. So anyway, there is a kind of agreement that this is overly pessimistic. Current policy scenario, so you see the top is here around 2050, but as I said, some people, some scientists claim that maybe that we anticipated the top, okay, current policies. And this is the scenario that corresponds to targets. So this is these three, the 1.5 pathway, which 1.5 was the Paris Protocol 2015. They basically identified actions for limiting the global warming to 1.5. Now we are at 1.2, 1.3. And then there is the pathway of 2 degrees, and this is 2.4. So these are the emission scenarios that are considered today. Usually climate model simulations are done for different scenarios. So you have the climate model simulation for business as usual. You have the climate model simulation for other scenarios. They are called, it's not indicated here, they are identified with the acronym SSP. I don't remember what is the meaning, so please have a look, but it is, okay, I'll tell you. And the business as usual is called SSP 0.5. And then there are other SSP with other numbers identifying different targets, okay? Let me just check because I don't like to leave a question unanswered. SSP scenarios, okay. Shared socioeconomic pathways. This is the meaning of SSP. And here you see a graph that is is a graph that is similar to this one. And you see 0.5 is business as usual. It's the highest one. And then there is 370 is the red one. I cannot associate now each one of these to the previous graph, with the exception of the business as usual. And the other ones, I'm not sure whether the red one corresponds to 2.4 or other targets, but if you read the Wikipedia page, you get any information. What is important for you, the key message? Climate model simulations are performed for different socio-economic pathways, namely emission scenarios, and the business as usual is considered to be overly pessimistic. And keep it in mind, because the media sometimes, and not only the media, continue to to make reference to the business as usual because they want to take a conservative approach. But on the other hand, from the point of view of an engineer, a conservative approach means more costs. And given that we are talking about social costs, an overly precautionary approach means an impact on people, especially the people with low income. And it is something that we need to avoid. And of course, we as engineer, or anyway, scientists interested in getting to target, we have the responsibility to get to target with the solution that entails the minimum cost for people and the minimum cost in terms of equality of opportunity and loss of diversity. Okay, good. And other forcing, precipitation, yes, of course. And we don't need to spend time on this. And forest greening and browning, and ice albedo, water vapor. I think this is something that you can explore yourself. It's obvious. I mean, it's obvious, and we don't need to get details on that. Just be aware of the meaning of what is albedo, and make sure that you don't forget it, because we are scientists, and therefore we scientists meaning that people studying science, and therefore we need to know some terms. And here in this graph you see also a picture of feedbacks, and it's important to know what is the terminology here: positive feedback, negative feedbacks, because it is not obvious. So positive feedbacks are those that we need to avoid. And positive means self-reinforcing, meaning that I have an increase. Let me give you an example. An increase of temperature, an increase of CO2, okay, due to human emissions. The increase of CO2 causes an increase of temperature. After an increase of temperature, the ocean reacts by releasing CO2. This is a feedback. It's a reply back, okay? And it is negative, it is positive, but the implication is negative, because it's a reinforcing feedback. The ocean releases CO2 and the temperature increases. And therefore, you have again another release of CO2. And maybe that you have humans putting air conditioning on, it's an increase of CO2 emissions. And this is a self-reinforcing feedback, meaning that the system reacts to an increase of temperature with another increase of temperature. This is called a positive feedback, but it has a negative implication. So don't make confusion. Positive means you see in red there, something to avoid. Negative feedback, clouds. You have an increase in temperature, increase in evaporation, increase in clouds, and the clouds cause a decrease in temperature. So it's a compensation. And this is called a negative feedback. It's negative because it gives a minus sign, you know, and on the red part, it's positive because it gives a plus. So self-reinforcing, compensation. Self-reinforcing is a positive feedback. Compensation is a negative feedback. So we have to be very much concerned by the positive feedbacks. Also in societal systems, we have positive feedbacks. And we have to be much concerned. On the other hand, let me see the next slide, because we are getting close. Okay, very good. On the other hand, the Earth system is dominated by positive or negative feedbacks. So should we hope that negative feedbacks prevail, the compensation of their system, the capacity of their system to compensate, prevail on the instability causes? Should we, of course, we hope for that, but should we rely on this assumption? Okay, let me just close with this consideration. The Earth system is resilient by definition. Nature is resilient by definition. If it wasn't resilient, we wouldn't be here. If nature didn't have a capacity large enough to compensate for shocks, nature wouldn't be there. Life is there because there is a capacity of the system to compensate. And the proof is that in the past, the Earth system underwent several shocks, very major shocks, like volcanic eruptions, like changes of the inclination of the Earth's axis, changes in climate, much more relevant of the changes today. So probably we are allowed to say that the Earth system has a high capacity to self-compensate. The same cannot be said for societal systems, because societal systems, they are very recent. So the current structure of the globe in socioeconomic terms, with the superpowers, and it's very recent. I mean, compared with the history with the human history, it's nothing. And so we cannot say the same for our current socioeconomic setting. But for the Earth system, we're allowed to hope that there is the capacity to self-compensate. Of course, we don't have to try, because, as we say, we don't have a B planet, planet B, and therefore we don't have to we cannot make a test, so we need to be precautionary. Okay, questions? Good. So see you on Thursday online. I will move forward with application of the R software and some exercises, very introductive, just to let you know. Okay. Good. Thank you very much.